Professor Rai Pala, and title is Hydrino Mediated Nuclear Reaction, Search for Experimental Evidence and Implication. It's very hard.
So
good luck.
Thank you. I would first like to thank the organizers for giving us the opportunity to present this talk here, and for all of you staying back, resisting competing attractions. So my partner in this adventure is my friend in the physics department. He's an experimental condensed matter physicist, and we are very fortunate to be able to work with very talented, passionate, and hardworking students. The student who contributed to this work is Nandita, and there are 3 other students who are in this conference. We also have a valuable partner in Professor Pankaj Jain. He's a theoretical high-energy physicist who is interested in modeling LENR effects. He really doesn't want to do anything to do with Hydrino, but we are the team that is involved in all this work in IIT Kanpur. You will see why he's not involved in this. So I would like you to indulge me in this. I'm a mainstream electrochemical group. We have a mainstream electrochemical group. With considerable difficulty, I've convinced the Electrochemical Society, Electrochemical Society, to have a special session in what I think is the most exciting electrochemical research topic. So there are 2 aims here. One is to bring all the CMNS groups in one place, and hopefully that will help us communicate to the rest of the electrochemical community. And another solicitation, I've been recently taken responsibilities as an editor in Nature scientific reports. So it's an increase in workload, but the hope is that I would be able to facilitate a fairer hearing of manuscripts in LENR. So I request you to consider submitting your work to this journal, Nature Scientific Reports. So I get, there is a chemical double entendre here. Okay, so I get 3 kinds of students. One are the students who like to work in mainstream electrochemical, fashionable topics in electrochemistry. We do a lot of electrocatalysis, batteries, and sensors. And there are these valiant students who work in LENR. 3 of them are here. They're presented already. And there are these hypervalent or hypervaliant student who is ready to work in so-called GUTCP and Hydrino. So you will see why I call them hypervaliant. And there are 4 classes of scientists. One is this community, LENR community, who have been mostly interested in heat excess via nuclear effects. Okay, so they don't really give a damn about Hydrino. They've not given a damn. And Dr. Mills, who is the person who is centered around Hydrino, and his reactor called the sun cell, suggests that he generates heat, excess heat, primarily via Hydrino, but no LENR. So we are a group who are exploring regimes where there are coexistence of transmutation, LENR, and Hydrino. We are exploring that regime. And there is the rest of the world who probably think that it's no LENR and no Hydrino. Okay, so the state of affairs is probably because of some of the convergence of improbables here. So LENR community, we want to overcome the Coulomb barrier. We do not observe intense neutron or other nuclear emissions. And interestingly, light water is also effective. Okay, so these are all really interesting things if true. So sooner or later, if you work in this community, you will get to hear about Dr. Randall Mills. There are these extremely well-written, semi-popular books. This is by a science reporter. This is written from a perspective LENR. So with a superlative title, right? America's Newton. Okay, so you would like to just get to see what it is. And there are 2 editions of it's a very good book with great illustrations by Brett. So he has a very, the second edition just came out a few months ago, okay? So these give a good introduction to the work of Dr. Randall Mills. So it's not just popular qualitative aspects here. So I was in graduate school, I was trained in computational quantum chemistry. I like to see things in a very quantitative manner. So he has this 2,000-page of 3-4-part monograph. It's a very mathematical, detailed mathematical theory. And what fascinated me was that I was trained in numerics, okay? So he was able to derive many things analytically. He gave analytical expressions for things which I thought could only be obtained numerically, okay? So that fascinated me. And even though I was trained in computations and theory, I didn't do the due diligence of deriving everything in the so-called grand unified theory of classical physics. That's his theory, because even without rederiving GUTCP, we went ahead because the implications of what he was talking about was astounding, and there was reasonable amount of experimental evidence to take it serious, right? So just to give you an idea, the creativity of this person is astounding. So he talks about a variety of things. At least there are 3 things that we should take very seriously. I'm trying to get the pointer working here. Anyway, all right. At least we are a community who is quintessentially curious about anomalies in hydrogen-loaded metal. We are interested in excess heat, and our group especially has been interested in nuclear transmutation. So even if you neglect many of the other things he's talking about, there are certain things that are very relevant to what we were doing, so we thought we should really explore. So why did we care to just extend this more? So this was based on not some new kind of equation. These were based on Maxwell's equation, but his assumption in a way is he assumes an extended structure of electron, okay? And his boundary conditions are set by non-radiating conditions. So this non-radiating condition I'm talking about is based on very well-founded physics. It was published in 1964 by GUTCP in Physical Review. We have to take it seriously. And I wish this was exposed to us in graduate school itself. Okay, so this is a very important result where you can have classical motion of charged particles without radiation. Okay, so his theory is based on these 3 aspects which sounded fairly reasonable. So the result of this theory is that he's able to derive subfractional quantum numbers, and these states of electronic states of hydrogen, he calls it Hydrino, all right? So just to give a qualitative picture here, so this is the largest sphere is the normal n equal to 1 state of hydrogen. So in this picture, electrons are not point objects, they are membranes, okay? So they're spherical membrane. So there's a spherical membrane surrounding the hydrogen nucleus, and they can assume states wherein these electron membranes can get closer to the nucleus, okay? So these are the Hydrino states. So you have subfractional quantum number that goes against quantum mechanics. So the Hydrino atom is comprised of a proton, a photon, which mediates the electric field between the electron membrane and the nucleus and the electron membrane. So that's this Hydrino atom. So his quantum numbers is 1 by p. They have electronic energies which are lesser than the conventional ground state derived by quantum mechanics. So they are formed by resonant non-photon mediated energy transfer. I don't want to get into the details. So that's a catalyst involved which can take up this energy, and because it's a catalyst, that can be re-derived. So there's a pathway to go towards these Hydrino states. So just to give you a more concrete example in terms of energetics, supposing we have a particular state of hydrino. So here I'm referring to P is equal to 3. So that involves a certain energy transfer to the catalyst. And this will involve certain energy release. And so the energy release with M is equal to 2 states, or P is equal to 3 states, is about 100 electron volts. So he has documented a set of catalysts which can give rise to different P states. And what is interesting is that we have a regime which, just to contrast it, we have the hydrogen combustion, electrochemical combustion has just few electron volts. So here we have a regime where the energy release is more than what you can get from chemical or electrochemical combustion, but less than nuclear energetics. Okay, so this is very, very relevant to experiments. Okay, this kind of energy regimes are observed in experiments. So I thought we should take it seriously. And he has also given detailed catalyst information on what can give rise to what hydrino states. So like many of us in this room, my first love has been quantum mechanics. So from the days I was a student, I've also asked this question, whether do we have a theory that is only computationally correct, or is it also ontologically correct? What I mean is that we have succeeded in having a computational framework in framing the Hamiltonian in a particular way, and extremely powerful framework that has given us great results, but does it also completely represent reality? That's what I mean by ontologically correct. So this theory of Dr. Mills is able to capture many things that quantum mechanics captures. We have done this due diligence. In addition, the GUTCP, the Grand Unified Theory of Classical Physics, predicts hydrino states that are not allowed by quantum mechanics. So the critical thing is that if hydrino states are confirmed experimentally, then we have to answer the question, is GUTCP both computationally and ontologically correct? So the critical thing is the experiment. Okay? So I personally believe the structure of electron, this is different from just electronic structure. If you go beyond the point particle picture of electron, holds the key for deeper connections between classical mechanics and quantum mechanics. There are more people more qualified than me to talk about this in the audience. There are a lot of data, but I want you to notice just few things. I've been doing computational quantum chemistry for 25 years. So we have done a lot of these calculations, so I think I'm right on computational quantum chemistry part. We have compared the highest level of computations available for things that are typically difficult, like dispersive interactions and so on. What I find is that there's a free code that can be downloaded. You should all try it out, called Millsian. And it is extremely accurate. Okay? It's computationally very accurate, and it's computationally very, very efficient. Okay? So these are the experimental results. I mean, I'm not able to use the pointer here. If what is indicated in the red, and that is the experimental result. Okay? So it's very, very computationally efficient and accurate. Okay? So GUTCP is computationally correct. The next question is whether it's ontologically correct, right? So why should we care? Okay, so we are a community which is interested in anomalies in hydrogen-loaded metal. So this is one of the crucial anomalies. We are interested in heat excess even with light water and without nuclear emission. And sometimes the hydrino may also appear like a fat neutron. You'll see why. So, and we've also observed magnetic fields in LNR. That's a very, very interesting paper that's been published recently. Fred Hagen is expert, has 30 years experience in EPR. He has worked with Mills to document these experiments. We should take them seriously, and it's been peer reviewed and so on. So, and also there are recently, just a few months ago, Dr. Mills has presented qualitatively at least Hydrino mediated transmutation. So you can probably take a look at that. So what are some features is one slide summary of his ways of thinking about transmutation. So the analogy is about as in muon catalyzed fusion. Okay. So in muon catalyzed fusion, the fusion enhancement is due to shorter distance between the electrons and the nucleus. So here also we are having similar effects. So if you have, let's say, dihydrino molecule at P is equal to 125, the dimensions are very much similar to that of muon. Okay, so it has fairly high vibration energies, so that can significantly enhance fusion rates. That's one way of thinking using hydrino. Yeah. Instability, and also there are some more details of its hydrino molecule, hydrino states. If you have P is equal to 127, so there is certain imbalance in forces because of which hydrino decays further. Okay, so these are all against standard model, but that's his model anyway. Okay, so it may lead to, okay, so it may lead to positron. The hydrino state will decay into positron and an electron and a pion. So we cannot get to the pion energetics with the detectors available to us. We were looking at, we can get signature of positron electron annihilation. So there are also other aspects of his theory wherein hydrino decay results in a gamma photon, which can also have photo-neutron production, leading to neutron capture and beta decay. So all these things were interesting enough to do the experiment. So one of my goals here to give this presentation is there are things that are sufficiently interesting. Can we do the experiments, okay? And can we also get feedback on the experiments? Can you give feedback on the experiments we are attempting to do? So there are, we are routine electrochemists. We can do all kinds of electrochemical experiments. There are relatively low temperature electrochemical experiments, but at high voltages and high currents that result in hydrino synthesis. We are looking at coexistence of hydrino and cathodes that display transmutation. We have close to 7 years experience in looking at transmutation in these systems. We are looking for hydrino signals also. We just got into 511, measuring 511 keV signals, which are supposedly because of hydrino decay. So importantly, Dr. Mills provides detailed synthetic methods that have been peer reviewed. Okay, so these are experiments that are accessible to this community. I request you to just consider doing them. Okay, some are higher temperature compared to routine electrochemical experiment. Some are very high current, which are like spot welding experiment. There are exploding wire, ball milling, and so on. Many of these things have been done by the LANR community, and he gives 20 plus characterization techniques. Okay, EPR, anti-Stokes. We are also trying to do many of these experiments and characterization. So in France and probably in Canada, we'll report a lot more of these things. Okay, so there's a fairly significant effort in our group trying to validate some of these things. So we started with so the hydrino synthesis is some videos. When we did the electrochemical experiment, we saw some precipitates that we thought might be hydrino compounds. So the first tool which we attempted was XPS. So we were initially excited that we saw hydrino 1/5 state, but unfortunately there's an overlap between potassium state and the hydrino 1/5 state. So again, this is not an unambiguous evidence. To Dr. Mills, potassium is a catalyst and sodium is not a catalyst for hydrino formation. So you can really contrast the experimental results obtained from potassium in the electrolyte and without potassium. We also did, in addition to this, we have a lot of transmutation results in nickel cathode that was presented over the course of this experiment. We tried looking for hydrino signatures in this. We have some hydrinohydride signatures, but I come from a catalysis background. One evidence is not enough.
1 minute only.
Yeah. So we have to look at a range of spectroscopies to say anything significant. Okay. So we really have to look at one system, not with just one analytical tool. We are trying to look at it with multiple analytical tools to say something significant. So these are all just preliminary experiments to advertise what we are trying to do and get some feedback. So we also looked at 511 keV signals with HPG detectors. Only one detector was working when we started these experiments. And unfortunately, what we observed was that the background actually had greater counts, okay, compared to the counts we saw during the electrolysis, wherein transmutation was observed. But later, when we looked at the experiments more closely, we had to get the backgrounds. When the experiment was going on, there was a lead brick which probably decreased the viewing angle to the detector. So these are very, very preliminary experiments, but just to give you an idea of what are the things which we are trying to do. Again, we are trying to do within a lead cave to go beyond the background. We are using sodium iodide detectors. Right now, we don't have any extra 511 signals, but these are the kinds of experiments we are attempting to do. So this is my last slide. So in summary, what we have within Hydrino is a well-established equation. We all are familiar with Maxwell's equation. The only new thing, in a way, is that in this view, the electron is an extended structure, which is probably shared by some of you here, and the boundary conditions are provided by a well-established physics-based topic, non-radiation condition. That gives rise to Hydrino. The Hydrino states are closer to the nucleus, so they may explain perhaps some of the anomalies which we observe in hydrogen-loaded metals. He has a lot of, Dr. Mills has evidence for excess energy without radiation, light water. We're trying to reproduce them. He has some explanations for the magnetic effects. Perhaps Hydrino states can be thought of as fat neutrons. Sometimes there can be a mix of these signals. We are also looking at a mechanism for transmutation using his theory. This is something that I request all of you to do. This is a freely downloadable software, which is very, very...
If you can make it some conclusion, it's okay.
Yeah. And this is my last sentence. So the crucial here is not, in my opinion, just to debate about the theory. We have to go to our lab bench. We have to try to synthesize the experiments and characterize Hydrino compound to categorically answer whether GUTCP is not only computationally correct, whether it's also ontologically correct. Thank you for your attention.
So, discussion open. Somebody? Oh, Conrad.
Okay. I would like to ask you, are there any predictions, some numbers? What is the probability for the transition from the usual hydrogen to Hydrino state? Because we need numbers, that it's not only, the idea.
So this is something, I have a physical chemistry background. I also wondered about the rates, right? You're talking about the rates of transition, is it?
Yeah, probability transition, this...
yeah, so he doesn't have a theory which gives you the rates of transition, but what he gives are the energy levels. There are very quantitative energy levels that have been predicted, which can be checked by experiments, but he doesn't have rates for transitions. But he gives experiments wherein the kinetics can be slow and kinetics can be fast, and gives qualitative reasons why they are so. But he doesn't have quantitative theory for rates.
You can produce some theories, and the probability for instance, for decay of the proton is 10 to 30 years, It's also possible, yeah?
Yeah.
But it's a problem of numbers.
Yeah, right now he does his nuclear transmutation theory do not have such numbers. You're right.
Okay, Bob.
Raja, thank you for a lovely presentation. Randall Mills is famously saying there's no low-energy nuclear reactions occurring in his experiments. You say you've had nearly a decade or so of observing transmutations, is that right?
7 years we've been working.
7 years, that's the best part of a decade. So in exploring this field, you're kind of doing a hybrid. Randall Mills over here, and maybe there's accidentally some LENR going on in the same thing. Are you actually linking the two?
I'm not a spokesman for Dr. Mills. We are an independent group. We are trying to look at if there is such a regime. Maybe there is 4 regimes, as I said, right? Hydrino only, That's his view. Our view is mostly LNR. We are interested whether there's a coexistence between the two. Yeah, fourth, you know.
Have you observed it in your experiments?
We are trying to do it. In France, I would tell you more precise answer.
Okay.
Okay, next.
I thought some experimental evidence should be interesting. So in one of our reactors, we have hydrogen flowing through it at a high velocity, and we are putting in, for example, 2 kilowatts, and we're getting out, say, 5 or 6 kilowatts of pure electricity coming out. And in this cell, we're not seeing any transmutation happening. It's pure electrical energy at quite high levels. And we found if we put very high voltages in, like, say, 30 kV, then we get beta and gamma coming out, X-rays and gamma coming out. But if we reduce the input voltage, say, for example, to 15 kV, then we see primarily just electricity coming out with some soft X-rays at 30 kV. So I thought you'd find that interesting. Maybe we could tie up and see what other emissions we're getting out that might confirm it's a Hydrino effect, because we're not seeing transmutation. Whereas if we add oxygen in there, hydrogen oxygen, it's almost always transmutation happening and heat being produced. So thank you.
Thanks, Ashley. We can surely discuss these. I'm interested in such regimes where we can exclusively see heat exist without transmutation.
Exactly.
And a transition to the other regime where you can see both. You seem to have such results.
Okay, next, please. Last one.
Hi, Raj. Wonderful presentation. And I like your statement where you want to put a math to whatever is happening. So we've got, like Hasselbeck, we do have the experimentation data for the last 3.5 years. But what is not adding up is the math. So we know how much of hydrogen has gone in. Probably none of them can be quantified. So we know the input can be quantified, but the energy that is coming out is definitely not adding up the math in terms of how many, say, electron volts are being generated in fusion. So if I give all this data, this is something that you can put a math to it, right?
I have been thinking about your situation. We can discuss this later. See,
Perfect.
the question many of the people, there are people who have been working for 3 decades. They've been trying to answer is, what is the fuel in LNR? Okay, that's it. Your question boils down to that. I have some ideas. We can discuss that. That may or may not be related to hydrogen.
Yeah. Perfect. Thank you.
Okay.
Sure.
So thanks again.
Thank you. Thank you.
Next speaker.